So, thank you, everybody, for being here, for the invitation to speak and so forth. You probably don't want to hear too much of a long introduction like that since we're at the end of the workshop. I'll get straight on with the talk. Okay, I'm going to tell you a little bit about roll waves. I was asked to review a little bit about roll waves, but I couldn't resist putting something in at the end, which is more directly about antidiffusive instabilities, and in particular, some things that come in that are not really about roll waves, and I'll explain why. So this is partly work with this cast of characters extending over some time. So let me first of all tell you what roll waves are. So according to Cornish of 1910, roll waves are these shock-like objects that form on fast-moving water conduits. They are high Reynolds number features. So they often appear in man-made conduits, but not always. So this is in a spillway from a dam in Wales, and this is from a place that's close to home for me. This channel is about 1.5 meters wide. It's in real time, and the frothiness of the water indicates that it's quite turbulent flow. So these waves, they appear and they travel for easily a kilometre or more. So nice coherent turbulent features on a turbulent flow. So that's a roll wave. They've been documented for centuries. Sort of the scientific discussion on them started with Cornish in In 1925, Jeffreys gave some theoretical description of that, but let me tell you a little bit about the formulation that he used to do that. So people have taken the roll wave phenomena and looked at it in the laboratory with laboratory flumes. So based upon some experiments by Brock in the 1960s, we redid some experiments. This is a 10 centimeter wide channel with relatively fast-moving water flow down it. You see these sequence of jumps, which are these shock-like roll waves. So you can look at them in the laboratory. In sort of a theoretical context, people have used the St. Venant model. So that's something that comes up in hydraulic engineering. You basically assume that you have strong turbulence. So what it does is it mixes the fluid up to the degree that you have a relatively blunt velocity profile. Thinking of it as a two-dimensional problem, you've got flow in which the velocity is almost plug-like because of turbulence. There's a logarithmic boundary layer at the bottom, and you write down conservation of mass, conservation of momentum for the fluid depth and for the velocity down the channel. So the St. Venant model is a sort of a mix of empiricism and dimensional analysis. You have the straightforward conservation of mass equation. The momentum equation contains gravitational acceleration down the slope, the angle's phi, and then there's some hydrostatic pressure gradients attributed to variations in the free surface. And the empiricism comes in with the effect of turbulence, which is basically this simple drag term. So just by dimensional analysis, the drag has to take the form of u squared over h, and then you throw in an empirical parameter in front of it. This is the Chasey drag law that's used in hydraulic engineering. So this is a nice simple model. There is a basic state where you have a uniform sheet flow. You can do a linear stability theory about that. So the mean depth and the mean speed are connected by the simple balance, because the thing's running downhill at terminal velocity in steady state. And you can do a linear stability about that. That's what Jeffreys did. Okay. So you perturb about that mean state, you do the usual linear stability analysis, and Jeffreys came up with this condition. and it establishes that if the flow is fast enough, then waves will become unstable. The condition can be expressed in terms of a dimensionless group with Froude number, which is u over the square root of gh. If that's bigger than 2, then waves are expected to grow. So those are the roll waves. Okay, so you can understand this stability criterion as roughly speaking, it's when if you create a wave, you increase the depth, then the friction is inversely proportional to the depth. So the friction goes down, so it gets faster, picks up fluid, and then continues to grow. There's a little bit more to it than that because the speed is also involved in the drag, and there's more refined arguments based upon kinematic wave speeds due to Whittam in 1974 that established what the physical origin of this instability criterion is. So let me tell you a little bit more about the linear stability properties. So when you look at the dispersion relation, which tells you what the growth rate is as a function of the wave number, then for the St. Venant model, once you're above a Froude number of 2, all wave numbers are unstable. So the growth rate looks something like that, which is a bit of a disaster because it means there's no scale selection for the waves. If you add a little bit of additional viscosity into the equations, so here you add a term which is du dx squared. And that gives you some short wave stabilization. So with that, a little bit of extra dissipation, a little bit of extra viscosity, the growth rate comes back down and you get a preferred wave number. And including that sort of a viscous term, that eases any nonlinear computations of the problem too, which I'll show you in a second. So it's customary to add things like this in order to regularize this instability and to ease numerical computations.
That's a question.
Yeah.
So your criteria doesn't depend on CF?
Oh, I should say one thing. I'm going to show you solutions of this pair of equations, nonlinear computations, and I will have expressed it in dimensionless form. All right? I'll skip the details of going through that non-dimensionalization. The important thing is that I'm going to use the mean depth as one of the scales, for the depth scale, and the length scale along here is going to be related to the depth, and then the speed scale comes from this balance, it's the mean flow, and that's where CF is. Right, so it gets hidden in that. Okay, so let me just now show you some nonlinear computations. So taking the basic state, I sprinkle in some additional perturbations. Here, I'm going to put in some random low amplitude initial perturbations about the mean flow. This is showing depth, the depth profile as those perturbations evolve. The Froude number is bigger than 2, so things are unstable. And I've got a periodic geometry. So I'm imposing periodic boundary conditions in X. So you see what happens is that waves grow. There is viscosity in the computation, so there's a preferred wave number. And that's what you see to begin with. If you look at a measure of the strength of the instability, it grows according to the linear growth rate, and then it saturates once these things get to some amplitude. They don't remain steady. There's then some nonlinear dynamics. You'll see that if I continue this computation, it's now shown as a space-time diagram here. So we've got the linear growth and initial saturation in there. What subsequently happens is that waves start to merge together. There's some merging events that coarsen the pattern. And at the end of this computation here, we've got 4 waves left, whereas there was perhaps twice that due to the linear instability. Okay, so roll waves, they grow, they saturate to some degree to begin with. The initial wavelength is set by the most unstable mode, but then there's coarsening. Let's sort of explore it a little bit more. I could carry on computations like I just showed you to go a little bit further in time. And for certain domain lengths, that coarsening just continues. So here's an example of that where we've started once again with some random initial conditions. Time proceeds this way. There's the linear instability. You see the wave mergers. They just continue until you've got a single wave left. And this is the roll wave that you get at the end of the day. Right, so these are computations with that viscous term in there. However, if you choose a very big domain, this coarsening doesn't appear to continue forever. It seems to stop. And the best way of actually exploring that is to search for steady states and then start initial value computations off with one of those steady states to see if it remains stable. So in this case, what we're doing is we're jumping into a moving frame with a single wave in it, single dome, in a big domain with a single wave in it, and we've jumped into the frame of the wave, and that's the red profile here, and we've sprinkled in a small perturbation on top of that steady wave profile, and what happens is that more waves grow. So you kick off with a single wave in the domain, but then other waves grow to disrupt that single wave, and you get a wave pattern with more waves in there. Right, so coarsening cannot continue to the longest scale in the system in this problem because it's unstable. And instead, you get something in between. So you see interrupted coarsening in this particular problem. That leads to some sort of a nonlinear selection of what the wavelengths should be. And we did some experiments, like I showed you a couple of slides ago, where you see this type of phenomenon. That's using a wave maker to trigger roll waves of a certain wavelength. And if you trigger roll waves that are too long, you see they don't survive. Okay, so let me try and rationalize all that a little bit more. So close to onset, you can do some weakly nonlinear theory. So if I take my Freud number and put it close to 2, epsilon is just some small number, then I can take the same banana equations and apply a multiple scale analysis to them to reduce the problem a little bit. And when you do that, it's a standard type of analysis. You define a new translating spatial variable. 2/3 is the wave speed at the onset of instability. You have a slow time, and you look at low amplitude waves. You end up with this wave equation. It's not a standard looking one, but this is what you get. There's a viscous term that's been included. It's suitably scaled, so this is a suitably small viscous term to engineer it to come in to the long wave, to this weakly nonlinear equation at just the right time. You can revisit linear stability with this, and there's the dispersion relation. The one thing that I'm going to point out is it just exposes the fact that for long waves, the growth rate grows like k squared. So it's this anti-diffusive instability. The nice thing about this problem is that you can search for nonlinear solutions. You get analytical nonlinear waves from it. Here they are. You look for a solution in terms of some traveling wave coordinate, some new traveling wave coordinate. This is directly what descends from here, and you can solve it to get this profile. It's just an exponential. But that means it's monotonic. So and I should say that I've discarded the viscous term in order to do this. So discarding the viscous term, this is what you get. You get this exponential profile, so that the only way you can build a wave is by having a piece of this exponentially growing profile followed by a shock, another one of these exponential profiles, and another shock, and so forth. So to build roll waves in this limit, where this viscous term is not there, you need to put shocks in there. So in other words, without that viscous term, the roll waves form shocks. And here they are. This red dashed line is a periodic wave train built from solving this particular problem without the viscous term. If you include the viscous term, you get the same sort of thing. It's just that it smooths the shocks out. So the important thing is, in terms of that idea of coarsening, is that at the back of the roll wave, you get this exponential decay to some uniform state. And as the wavelength gets bigger and bigger and bigger, this level converges back to the original mean flow. So it's no surprise that long roll waves become unstable again because they contain this big wide gap between the shocks, which suffers the same roll wave instability that led to them in the first place. So that's why you cannot coarsen forever, because ultimately you end up with the same instability. Okay, so that's enough about turbulent roll waves. Now let me tell you about laminar roll waves. So there's a different version of the problem that sometimes is called the Kapitsa problem, which is basically the laminar version. And you're all very familiar with it because whenever it rains outside, you see roll waves on your windscreen or on the gutter on the road. These are these waves, these smooth waves. The Reynolds numbers are clearly much smaller because these are nice smooth films. So here's a picture from a road somewhere. This is some images from an original paper by Kapitsa and Kapitsa. I'm looking at this in the laboratory. You'll notice that the date is after the turbulent one. So this is an instance where the turbulent problem was discussed before the laminar one. In this case, the important thing is the Reynolds number. It's a classic kind of fluid stability problem. It's the Reynolds number that becomes important when you go through the analysis of the problem. You can do that by looking at the Navier-Stokes equations and doing a long wave kind of linear instability analysis, and you end up with a criterion that says that the Reynolds number of the flow has to be bigger than some critical value. And that goes back to Benjamin and Yi. So further from onset, if you want to build, theoretically, wave profiles like this, people have done that, and it has to go through various approximation techniques if you're going to start with the Navier-Stokes equations but try to simplify them. But people did that. There's some sort of averaging type techniques that people have used, and what they end up with is a pair of equations like this, where you've got a conservation of mass equation and a conservation of momentum equation. You know, h once more is the thickness of the film, and u is now the mean flow. The momentum equation contains the gravity terms again. It's got some mixed up kind of advection of momentum equations because there's actually a flow profile in the film now. So it sort of messes up how momentum is advected. And then there's a drag term. And the drag term's now got the viscosity in there. But otherwise, this is very similar to the St. Venant model. And people have used that model to look at capillary roll waves at the nonlinear level. So now let me explain what I mean by a roll wave and what I mean by an analogy to it. So basically, the idea is that there's a whole bunch of phenomena that you might call roll waves, and they're unified by the fact that people have come up with a conservation of mass equation and a conservation of momentum equation that has a similar form to those two that I showed you. Right. This is the mass equation, the momentum equation. This is now in some dimensionless form where I've identified something like a Froude number. Right. There's sort of mixed up advection of momentum. There's the gravity terms, and there's some drag term. Right. That's the sort of the basic structure of the St. Venant model and that laminar version of it. So with this type of a model, you can do the linear theory all over again, and you get some criterion on the Froude number, just like Jeffreys. So this establishes that if things are fast enough, you'll get an instability. So there's a sort of a common theme for the linear instability, and following the Witten type arguments, you can come up with some similar physical mechanism behind it. And moreover, you could redo that weakly nonlinear theory too, to indicate that the dynamics should be similar just beyond onset. So that's kind of a theoretical argument that says that these things should be sort of unified. Right, so having said that, now let me tell you about some analogues. So, first off, mud surges. This is a picture of the Yellow River, where you see these sharp jumps that are formed upon it that are propagating down the river. So this is in some state where the water has picked up a hell of a lot of sediment and it's just traveling basically as a mud. The mud's a sort of a non-Newtonian fluid, perhaps a yield stress fluid. So the question is perhaps this is the roll wave phenomenon. It's a laminar phenomenon, but now in a non-Newtonian fluid. This is some pictures, courtesy of Christoph Ansi, of possibly the same phenomenon in Switzerland. You see the destructive effect of roll waves in mud. It's not completely clear whether these are intrinsic flow instabilities or caused by some pulsing of the source. Right? That's not recorded in this context. But anyway, that's sort of what they look like. Right? So is this, there's two of them here, that suggests that it is a sort of an intrinsic instability. You wouldn't want your house to be close to any of these. Okay, so here's the laboratory version of that with some kaolin suspension. That's some clay suspension. That's recorded a similar type of thing. So here you have to modify those kinds of models. The drag term is going to have to represent the non-Newtonian properties of this material. Here's the same thing in a flowing granular medium. So these are experiments by Forter and Paulicon, or Nico Graysgrip, where you basically pour sand or glass spheres down an inclined plane and you see roll waves. People have suggested the same thing happens in bubbly fluids. So I guess the lighting doesn't come out so well, but if you've ever sat next to a freshly poured pint of Guinness, then you'll notice these descending waves in the bubbles. And you'll see then they kind of layer a little bit. This is a picture of an art installation that was in a Canadian museum. So you basically got a tank with divisions in it. There's a whole bunch of bubbles that are injected at the bottom, and they rise up these divisions in these gaps, and they form these slugs. So those have been likened to roll waves, and people have come up with equations just like those roll wave equations to describe them. People have also suggested this to happen in various kinds of traffic flow problems. This is a little less clear. Normally for traffic flow you have a kinematic wave equation, somehow you need two in order to get the roll wave phenomenon, but it's been suggested there. Flow down collapsible tubes. So if you take a tube with an elastic wall, you have flow down it, the tube can collapse a little bit, and people have observed the roll wave phenomenon in this particular context. So let me just quickly go over what the two equations are. You have conservation of mass. The thing that's important now, instead of the depth, it's the area. Then you've got the conservation of mass. You've got pressure gradient that forces flow. Somehow that's got to be related to the area of the conduit. And there's some drag term. So you need some prescriptions for those two things. And that comes from doing the physiology of the blood vessels or so, and we've got Tim Pedley, who's an expert in that kind of stuff. So here's a paper where this was considered for a relatively long tube, and the roll wave phenomenon was considered in that particular context. It's also been thought of for a relatively short tube where you don't really care about wave propagation, you just think about a relatively short section of this, and so somehow you want to divorce yourself from the effects of propagation and just look at things varying over a short section, and then you end up with thinking about a problem that's really a set of ODEs rather than PDEs in the x coordinate. So you do some sort of a lump parameter model. And that's used to explain things like Korotkov sounds, which are sounds that you hear with a stethoscope when you're taking blood pressures. Okay. I hope I didn't butcher that too much, didn't I? So, and the direct analog of that is volcanic tremor. So a fellow called Bruce Julian in 1994, he pointed out that you could possibly explain tremor, volcanic tremor, in the same way. So these are some signals which have been recorded from a volcano in Costa Rica. Sometimes it's quite harmonic, sometimes it's a bit more chaotic, but it's ground vibration, and it's associated with the subsurface flow of magma. And the best interpretation for it is that you basically got a little conduit with rock walls, but they can move, and as the magma flows through it, it excites vibrations. And what Julian did is he wrote down an ODE model, just like that lump parameter model for Korotkov sounds. But you can sort of extend it and think about it as a long conduit and come up with a sort of a roll wave instability analysis of it. And there's a whole bunch of interesting things here that's going a little bit too far for the present context. Okay. So, those are a gallery of analogues. So what I wanted to do in my remaining time is to talk about a slightly different phenomena. So I'm actually interested in a case where I have non-Newtonian fluid, but I don't really care about inertia. One of the important things about the roll wave phenomenon is that you need those two equations. You need the momentum equation with its inertial terms. So inertia is a key feature of the roll wave problem. However, it's possible to get wave instabilities in these flowing layers without inertia, due to the non-Newtonian material behavior. And I'll give you two examples of this. One is thixotropy, and the other is discontinuous shear thickening. Discontinuous shear thickening, I'm thinking about a cornstarch suspension, oobleck. So we've got a thixotropic fluid and oobleck. Two particular examples. I need to explain what I mean by thixotropy first, and then I'll talk about the other one. So, in non-Newtonian fluid mechanics, there are certain kinds of materials where the most important thing you believe is that the main impact is how the material structure changes the viscosity as you make the material flow. And the way that people describe that in a simple way is to imagine that you have steady, spatially uniform conditions and you plot the so-called flow curve. So you've got the strain rate or the shear rate or the deformation rate against the stress. That's the flow curve. And in the simplest settings, you imagine that there's a curve and you're following some curve on this plane. That's what you do if you have a Newtonian fluid. For a Newtonian fluid, it's a straight line, goes through the origin, the slope is the viscosity. There's a simple yield stress fluid where you have an intercept. That means you've got to surpass a threshold before you make things flow. That's a yield stress. Right. The thixotropic fluid, or this other one, they're a bit different because the flow curves are not monotonic. So, the thixotropic fluid is something like this. We've got a flow curve that has a shape somewhat like that. So imagine the thought experiment of taking a rheometer, for example. In a rheometer, what you have is you've got a plate, and then you have another plate, or a cone. You put the fluid between them, and then you spin the top one, and you measure the torque. The torque is like the stress. The rate at which you're spinning it gives you the strain rate. So you can imagine increasing the torque, that's increasing the stress. So I increase the stress, so the flow curve starts up, going up to there, then it goes down like this. So if you were to be increasing the stress, you go up here, nothing would happen, right? You wouldn't be putting enough stress on the thing to get the thing to spin. You reach this particular point, all of a sudden you've got to zip over here to the other branch of this flow curve, and then you keep going up. Now I decrease the torque, I come back down, I follow this branch until I reach that point, and then all of a sudden I have to stop and come back down like that. So in other words, I get this hysteretic pair of flow curves. That's the hallmark of thixotropy. Different kind of scenario is what happens for things like cornstarch. So recent work, including Mike Case's stuff, what you argue is that as you increase the stress or the strain rate, at some point you reach a critical threshold and all of a sudden things dramatically increase in strength. Discontinuous shear thickening. All right, so let me explore the consequences of these two kinds of rheologies in the inertialess stability of a flowing layer. Okay, so thixotropy. Let me expand upon thixotropy and where I got this shape from. So for thixotropy, it's been common to try and describe things in terms of a microstructural order parameter. Let's call it lambda. So you basically just write down some sort of a reaction equation for it. You say that d lambda dt has got some restructuring term minus a destructuring term. The restructuring term is like natural healing. There's some rate associated with it. It's the rate at which the structure wants to form itself. But then the destructuring is because of the fact that you're forcing it to move. And the rate there is just given by the shear rate. So you've got this competition between restructuring and destructuring. In steady state, there's a relationship implied here between this microstructural parameter lambda and the shear rate. And along with that, you need to come up with some formula for the viscosity. So there's some relationship between the stress and the strain rate. And the viscosity depends upon the amount of order. So your viscosity depends upon lambda. So with this simple algebraic model for the restructuring, the destructuring, and the viscosity terms, you basically come up with a flow curve. Right? You eliminate lambda and you get stress versus strain rate. That's what this curve is. And so there is a state out here. That's where it's flowing strongly. That's where things are getting strongly broken down, destructured. And then if you get over to this side, that's where things are becoming structured. So, because we've now got an evolution equation, we can interpret, in some sense, what the stability of these various branches of the flow curve are, and you can establish that this bit's unstable and this bit's stable. So when you have a descending flow curve, the implication is that it's kind of unstable and everything will go terribly wrong there. And this is a stable branch. Okay, so this is a sort of slightly different version of what's been written down previously. The only difference is the algebraic forms that I've adopted for, say, the viscosity and so on. The important thing is it's a fully structured state where lambda is lambda 0, and that means that the viscosity is diverged, right? So down here it has to be at 0 strain rate for that. And then there's a fully destructured or distorted state when this order parameter goes to 0. Okay, so you solve that, you get this parameterized flow curve.
Technical question.
Yeah.
The equation for lambda, the shear rate enters only in a term that multiplies shear rate and lambda. You would think if you had, a suspension of almost anything, then merely imposing a shear rate would produce a certain amount of lambda, in which case you would want a term with a gamma dot but no lambda, wouldn't you? Meaning, after all, if you have a suspension of rods or something, and you shear it, then on average you produce some amount of alignment along the extensional axis. What that means is you'd want a term in which gamma dot alone appears without a structured parameter.
So, so there's various models that have been written down here where there are a lot more general forms acceptable there and there. And so physical settings, like what you're talking about, are probably contained in all of that, which is what's in this type of paper. Here, the interpretation is that really you've just got an exponential rate at which you're decreasing, and the rate has been dimensionally estimated in terms of the shear rate. That's simply where that came from, right, which is sort of the interpretation in here.
I see.
Okay, so it's one specific case, and I'm just going to adopt this as an example. Okay. Good. Okay, so I'm going to assume a shallow layer. I have no inertia. So in a shallow layer, the force balance equations basically boil down to these two. So the equation normal to the plane underneath, we basically just have hydrostatic pressure. Right? In the shallow layer, that's the main balance. This is Reynolds lubrication theory, and it's what you use for, say, a viscous gravity current, a shallow viscous gravity current. Okay, so in this particular geometry without inertia, you end up with a hydrostatic pressure, and then the momentum balance down the incline, it's a balance between the gravity that's pulling you downhill, any hydrostatic pressure gradients acting in that direction, and then these are all resisted by the shear stress. Okay, the vertical derivative of the shear stress. So the momentum equations get very simple in this particular limit. You can integrate them. So you specify the pressure and you specify the shear stress. Okay, so this is like a stress specified system. So what it means in the particular context of this thixotropic fluid, if you think about the flow law, the stress is maximum at the bottom. So the stress has got to get above there if you're going to force the thing to start moving. Right, so let's imagine that we have a plane with a layer of this fluid on there. So to set things going, I can tilt it, tilt it, and still it starts to move. And then I can tilt it back a little bit to try and get it into some steady state. So I've tilted it to get it moving and then go back a little bit. So what that means is at the bottom, I reached this point and went beyond it. So the bottom of the fluid, there's a bit at the bottom of the fluid that went over to here. But at the top, there was no shear stress because it's next to the top surface where there's no stress. So the bottom's still down there. Right. So the thing's naturally going to divide up into a bottom layer where it starts to move, it destructures, and then a top layer where it's still fully structured and plug-like. And then in between, if I go through this exercise of doing that, there's going to be this division, right, that separates the two layers, and that will act like a material surface. Because it's going to be between, it's going to be somewhere between there and there. So we can set the problem up so that we've got a flow state that looks a bit like this. We've got a lower layer. Right, that's the destructured layer. It's happily deforming. Then we've got this bit on the top that's structured, remaining the structure. Okay. So once we're in that sort of state, I can then consider this type of linear stability analysis again. I look at the fate of a wavy perturbation. So let me think about doing that. Just to get some simple results, I'll make one further assumption. And that's going to be that I'm going to say that the structure, the microstructure, that responds relatively rapidly. So in other words, in this lambda equation, it evolves relatively rapidly, so somehow these time scales associated here and here, they're sufficiently quick that it goes to steady state. So in other words, I reach this branch or stay on that branch very quickly. So in that particular limit, you can come up with a reduced model relatively easily as follows. So I've got this picture where I've got the two layers. This is my layering. Over here, I'm on one branch of the flow curve. Down there, I'm on the other branch of the flow curve, right? There's a branch, zero strain rate, and the branch on the right. So the branch on the right, because I've got rapid relaxation of the microstructure, I can say that lambda is a function of tau, gamma dot is a function of tau. Okay? Gamma dot's the strain rate, right? So gamma dot here is basically given by du dz. The stress is proportional to the stress at the bottom. Zeta here is just that profile factor. Here's the stress at the bottom. That's this lubrication model, right? So from all of this, I can just integrate this to get what the flow profile is. But what I'm more interested in is the flux. So I would like to calculate that. Just by a simple integration by parts, I can instead look at this. That being du dz. And then if I just take my flow curve from here, take this, pop it in there and convert it to an integral in tau. So I get some relatively compact description of what the flux is given the flow curve. So it's sort of somewhat insensitive to the algebraic details of that Thixotrope model. But anyway, then I can come up with some evolution equation for what should happen. And it's basically just mass conservation for either the total layer or for the layer at the bottom, the destructured layer. So h is the full depth, h is the depth of the layer underneath, and they've got their own fluxes through there. It's the same flux function. But anyway, you've now got a pair of evolution equations in this inertialess limit. There's some simple mean flow state. Linear perturbations to that state can easily be explored in this pair of evolution equations. And what you find is that there are unstable modes that depend upon the rheological parameters. So here I've chosen some rheological parameters where there's an instability. The instability has a growth rate as a function of k that looks just like the roll wave one. It grows and saturates. There's a second one because we've got two evolution equations. That's always stable. And there's some phase speeds associated with that. They're quite constant. That's helpful because you can then jump into a certain moving frame in order to see things growing more easily. Okay, so a quick bunch of computations. That's with three different initial conditions. The same choice of parameters as that growth rate plot. And here I've got some random small initial conditions to grow into four waves. The coarsen is taking a mode 3, stays as mode 3. Mode 5, it coarsens. This one would carry on evolving and maybe coarsen too. That sort of looks a bit similar to the roll wave problem, right? But it's actually quite different. If I look at the solution, this is the solution for the thickness of the lower layer, the big Y. So this is what it would look like if you actually looked at the thing. So this is the lower layer, that's the full layer. The solutions that you get at the end here, the waves are all at the interface. Right? The top surface has a reflection of what's going on in the interface, but it's much smaller. So these are really interfacial instabilities. Right? And in fact, the analogy is not really with roll waves, it's with viscously stratified flows. That's where you've got two-layer flows with different viscosities, and it's known that if you put the more viscous fluid on top, you get interfacial instabilities. That's precisely what we've got here. So in this particular problem, the rheology can prompt this kind of viscously stratified instability. You haven't got time, I'll mention something about that later. Okay, so the other problem, cornstarch. So I was interested in this quite a while ago because John Bush showed me a picture that was in Simpson's book on gravity currents where he basically poured custard down an inclined plane and see these very impressive waves forming on it. And when I visited John, we thought about this, and there was quite a mystery associated with it, which is the following. So let's assume that we're dealing with a viscous fluid. If you don't know what the viscosity is, you can kind of use rough dimensional balances to say what the Reynolds number is anyway. So the viscous stress has to balance the gravitational force downhill for a flowing sheet. So you've got the gravity term, the viscous term, they've got to be in balance in steady state. And the viscous term contains the fluid depth and the mean flow speed. So from this balance, you can then estimate what the Reynolds number is. It's u squared over gh sine theta. Theta is the angle of the plane here. So with that, you can estimate what the Reynolds number is. So if the Kapitsa problem, if you look at typical conditions under which those Kapitsa wave form, it's for a depth of a few millimeters, u of tens of centimeters, say, slopes of 10 degrees, tells you that you need a Reynolds number of about 10 degrees, which is consistent with that stability criterion. For cornstarch, you do the same thing. The phenomenon is the following. Repeating the experiments in the lab. So this is a 10 centimeter wide channel, and Alison Rust is in the background, and we're pouring these cornstarch suspensions, this custard thing, down the channel, and you see these spectacular waves, right? The speed and the depth associated with that, given that dimensional balance, suggests that the Reynolds numbers associated with this are really small, less than 0.1, right, which is very different from the roll wave phenomenon. And so we tried to understand this, and we failed miserably. So it's observed that it's a relatively low Reynolds number phenomenon. It's got to have something to do with the rheology. At the time, what was available was knowing what happened when you had a shear thinning fluid. That's something that as you increase the stress or the strain rate, it gets weaker. That's destabilizing. Viscoelastic was also known to be destabilizing for roll wave type problems. So we were envisioning this as a roll wave problem, right? But cornstarch suspensions are shear thickening. Oobleck is shear thickening. You can run on it in the swimming pool, right? It doesn't show too many effects of viscoelasticity. You wouldn't naturally think about this as a typical viscoelastic fluid. So neither of those seem to be the explanation for this, and we tried to think about some other things, and we failed. However, Texier et al. Very recently pointed out that there are some relatively new constitutive models of these types of materials that could explain this phenomenon. So, discontinuous shear thickening rheology. What's that? Well, you've got the idea is that you have a suspension of particles, and they have some short-range repulsive interactions. It keeps them apart. And it keeps them apart as long as you're not pushing them together too much. So they're happily to sort of move sedately around each other and maintain a relatively low viscosity until you jam them together by pushing too hard. And then when you jam them together by pushing too hard, they come into contact, you generate a lot of friction, and the resistance massively goes up. So here's a model due to Weyalt and Cates, where you have a volume fraction phi. There's a bunch of other parameters in here. You say basically that you've got the shear rate is a function of the stress in a way that depends upon this volume fraction. For low volume fractions, here's what the flow curve looks like, much like a Newtonian fluid. But if you have too many particles in there, if the volume fraction is too big, it's actually drawing it the wrong way around, right? This gamma dot is a function of tau. This is tau against gamma dot. And you end up with this non-monotonic flow curve. So the idea is that as you're going up here, if you reach that point, all of a sudden you've got to shoot up. That's where it's jamming together and thickening. Okay, so the consequence of that on a sheet of fluid flowing down a plane would be the following. At low volume fractions, you're going to have a flow profile for a laminar viscous-like film, which is sort of the usual parabolic shape. But as you increase the volume fraction, at some point, the bottom is where all the stress is. Right? At some point you reach a location close to here, all of a sudden it really thickens up, so the bottom of the fluid becomes arrested. Then you get this kind of localization of flow to the top. So that's what's going to happen for the mean flow. But Texier et al. Pointed out that this could also be the source of the instability which generates those waves. That's their own version of the experiment. Okay, so you can go through the lubrication theory again. It follows the same pattern, except now there's only one layer. And you've got the same force balance equations. You calculate the flux, which depends upon your constitutive law, plug it in, and you end up with your mass conservation equation, which is like this. This G function, that's the thing that's an integral in stress of the flow curve somehow. Right, so it all gets channeled into there. This is this Weierarch-Cates model of the rheology. So you shove it in there, you get this. And you can go through the linear stability analysis of that, looking at small perturbations about the mean flow. This is what you get. There's an advective term, and there's an antidiffusive term, provided that function G, here, this integral, provided this derivative evaluated for the basic state. In the basic state, things are scaled here so that the stress is 1 at the bottom. So G prime to 1. Provided that's negative, you would get instability. And you would get an antidiffusive instability. And so that's exactly the G function. And looking at G prime to 1 against this volume fraction phi. Right? So as you get higher and higher volume fraction, you approach the shear thickening transition, and this predicts instability. It's not quite, this stability criteria is not quite related to the derivative of the flow curve, which is what you might expect purely from the flow curve. Okay, so this actually provides an explanation for that instability phenomenon observed in those flowing cornstarch layers. But now, having sat through a number of talks in this workshop where people have talked about N-shaped curves or S-shaped curves, you know that that's not the complete story, because this implies an ill-posed mathematical problem. There's an ultraviolet catastrophe associated with the fact that the short waves are all much more unstable. Right? In the roll wave problem, we had the growth rate coming up and flattening out. That was one problem, but this is even worse because the growth rate's diverging with the wave number. Right, so somehow there's an ill-posed problem here, and there's no wavelength selection mechanism. In fact, one of the things that's completely clear in the experiments is that there's a pretty well-defined wavelength. So there's definitely some open problems here. Texier et al. Appreciated the fact that there were some issues associated with the negative diffusion. One possibility is to try and add inertia in, but this is really slow flow. Another possibility is to make the rheology time dependent, to allow the frictional contacts that are building up the viscosity to somehow relax in time rather than instantaneously change the viscosity. That makes it much more like that thixotropic model that I wrote down to begin with. Anyway, at the moment, you know, they gave an exploration of this model in that particular context, but there's still no explanation for why you get the wavelength. Okay, so now I summarize. I traveled a long way to come to this workshop, and then got a horrible cold at the beginning of it, and there's a long way to come for that, but fortunately the online system at the Isaac Newton Institute made it possible for me to sit in my room and watch all the talks. Anyway, fortunately I made it to my own talk at the end. So I reviewed roll waves and their analogues, and they appear in a whole bunch of contexts. I tried to indicate what I meant by an analogue by saying that there's this common theme, mathematical theme, and that just unifies the mechanism and linear instabilities and so on. So, some interesting questions that I pose to you. What are they telling us about rheology? Well, you see the phenomenon, and you try and import a simple constitutive model into the fluid equations to look at the consequences of that, and it doesn't look like it completely explains everything, right? You have to start talking about relaxation and microstructure. And those thixotropic models, they are often just made up with phenomenological arguments. The roll waves or these inertial instabilities themselves, they're telling you something about the microscopic behavior of the material. In particular, can you come up with some insights to avoid those short wavelength instabilities? 2 minutes left, but that's the questions, isn't it? I've gone overboard. I do apologize. Thank you.
You started a couple minutes late, so we know you can give you a couple extra minutes for questions.
Okay.
Who would like to start? Ben.
So for your first part about the inertial roll waves, so is it obvious that when you reach this very non-linear stages, the Saint-Venant approximation is correct? What happens close to this shock?
I think it can't be, right? I think it's crazy. These whole shallow layer approximations are assuming that the free surface slopes are small, and the minute you've got a shock in there, clearly they don't work.
So what happens there?
There's not been too many works that explore that. It's a turbulent flow, so it's kind of hard to just proceed numerically and explore what happens numerically. But I don't know if anyone's tried to do it. I've seen some models where they've abandoned the shallow layer approximation, but I don't think you would really call them genuinely turbulent models either. In the capillary roll wave problem, people have certainly looked at the nonlinear waves where you abandon the shallow layer approximation. And yeah, you get kind of substructure in the roll waves.
Right, John, you had your hand up next.
My question is based on my ignorance of this area, but long ago, when I was young, I remember there was a paper by Benjamin and Lighthill, 1954, flow down an inclined plane.
Yeah.
How does that relate to this?
Well, that's...
Is that, maybe I just missed it.
Yeah, so that is definitely connected to... It was a precursor to this.
Right, okay. Right.
So it's also reflecting perhaps ignorance. If you, in some sense, is there any kind of consensus or understanding of how much turbulent mixing occurs when you propagate one of these through a region? Right?
The turbulent roll waves.
Yes, exactly.
Yeah. So actually, I didn't mention that. So Cornish, I guess, was probably a hydraulic engineer, and there's a practical concerns with the whole thing.
That's the sort of person who'd be concerned.
Yeah, yeah. So there is a literature on roll waves which is about the practicalities of what they can do in man-made conduits, whether it's to do with turbulent mixing or the fact that they can be quite destructive if they hit an obstacle. So there is a literature on that.
Is it empirical or has it progressed beyond?
I think it. Well, there's textbooks that talk about it, but only in a largely empirical sense, I think.
There's a question in front.
Yeah, related to the shock structure. Yeah. So I have thought like hydraulic jump. So the amplitude of discontinuity can be determined by the amount of dissipation of energy.
Yeah.
Then I still wondered, so the role of viscosity and also turbulent mixing in your argument. So
in this particular problem, when you go through and you look at the Saint-Venant equations, or you look at this weakly nonlinear model, the amplitude of this thing is dictated by the wavelength. So the dashed line, there's no viscous dissipation here, right? But there's drag. There's drag in the problem from the bottom, right? But the jump height is dictated basically by demanding that it's got some periodicity. Right? The thickness of the thing, that's controlled by the viscous term. So it's not as if the jump height is actually something that's dictated by turbulent dissipation in any way. At least in this model, or the St. Bernard model.
Okay. Okay, thank you.
Is it quick?
Yeah, sure.
Sure. One last question.
Yeah, if you go back to the very first version of this problem you wrote down with the turbulent bottom drag u squared over h and so forth, if you took an equation like that and just added a bit of velocity noise and numerically looked at the steady state, is it a patterned, regular, striped steady state or anything like that, or is that not known?
I'm not sure what you mean.
Meaning, say, you take the PDE and just ask if there's a statistical steady state that sets in.
If you...
Maybe with a bit of noise, something just that it allows it to explore configurations. Do you get some sort of spatially periodic, organized steady state?
Well, it's going to depend upon the Freud number, right?
No, beyond the instability.
Okay,
Yeah.
so beyond the instability, if you add noise to it,
Yeah.
oh, I can tell you that.
Oh, good.
Okay, so this in the St. Bernard model, this is a convective instability. So you see it in all of the computations because I've chosen periodic boundary conditions. But if you don't, then what happens is that it just gets washed out of the domain. So you have to like keep on triggering them if you want to see them with boundary conditions. And in this particular case, that's where you just kept feeding them at the top boundary with a bit of noise. So that's what would happen with a bit of noise. And so it does select some typical exit wavelength.
It does.
Right. Is that?
Okay, it's partial answer. Thank you.
Okay. Let's thank Neil again.